Hello everyone. Today we are going to talk about statistical analysis of output from terminating simulation. But before we begin, let's talk about time frame of simulation models. And there are two types of simulation models in terms of time frame. One is a terminating simulation. So in this case, the model itself has a specific starting and stopping conditions, and definitely run length should be specified or well defined. Another one is steady state simulation model. So in this case, we need to run the simulation for a really long time so that initial condition cannot affect the result, okay, output of the simulation model. So technically, it's possible we want to run the simulation model forever, but that's that's impossible, right? In real world. So basically, we need to provide sufficient time to make the older simulation output stable. Okay, so that's why initial condition in this case in steady state simulation model won't be matter. Okay, then you may wonder how we can actually differentiate these two simulation models. Okay, then actually there are the way to collect the statistics is different. Okay, so let me explain the characteristics of these two simulations in detail. So terminating simulation, let's talk about the terminating simulation first. So in this simulation model, you should have the specific starting and stopping conditions, right? So the subject system also should have specific starting and stopping conditions such as restaurant, like a service shop, and so on, right? So if you think about the restaurant, it open at 9 a.m. or 10 a.m., right? It has a starting time, and also it has the closing time, right? So in that case, you can actually utilize this termination simulation, and good. And this kind of restaurant, or service shop, should also, in order to evaluate the performance of the restaurant or the service shop, you also want to consider the idle state, right, at the beginning of simulation, right? When you open your shop or the restaurant, and initially it is empty and idle, right? However, you don't want to remove that kind of performance, ignore the performance during that time. So warm-up period is very matter in this simulation, and uh, warm-up period is also known as the time that the system reaches each steady state from each initial state. Okay. However, in terminating simulation, we want to consider the warm-up period as well to evaluate the performance of the system. Okay, so there are two ways to put the stopping conditions in Arena. One is that you can actually specify the replication time. Okay, so for example, you can set up the replication length basically in Arena. Okay, so that the certain office or certain restaurant can close at a certain time. Also, another way is that you can specify the number of entity can be finished or alive or the entities finished or alive or departed and so on. So in that case, for example, we can close a store with the first 100 customers or with the thousand of customers and so on. Okay, where you can close your manufacturing facility if you produce 1,000 items in a day, something like that. Okay, you can specify the closing stopping condition based on the number of entities leaving your system or entering your system and so on. So there are two ways to specify your stopping condition or stopping conditions of the simulation model. Okay, that's a termination simulation, and then terminating simulation, and next one is a steady state simulation. So basically all the performance measures in the steady state systems, okay, should be stabilized, right? That's why we have to run the simulation model for a really long time. And stable system In stable system, we also have assumption that the traffic intensity is lower than 1, which means if a traffic intensity is greater than 1, and that means you will have a error message in Arena because your queue will have an infinite number of entities. Okay, so your service rate should be better than or faster than the incoming rate, okay, or level rate. Okay, so it should be stable. If the traffic intensity is greater than 1 equal to 1, and then your system will actually have overflow, so it cannot be stable. Got it? And in this case, we need to ignore the initial conditions. Okay, especially those initial conditions should not be a part of the simulation result. So that's why we need an additional technique to remove the statistics collected during the warm-up period. Okay. And when we use we use a steady state simulation, especially when we want to analyze consumer behavior during the peak hours, or performance of the manufacturing facility during the peak hours, something like that. All right, so let's talk about output analysis. But in this class, actually, we will mainly use terminating simulation. Okay, so let's talk about the output analysis for the terminating simulation first. So in order to collect the output data in the arena or a simulation model, you have to make the IID replications. So independently, identically distributed replications. So in order to do that, you can actually go to the run setup in arena and just change the number of replications in arena. Okay. And Arena will, or the other simulation software, will automatically correct the IID applications for you. So I conducted the IID applications and then collect the data. Okay, so we can avoid the bias with the random statistical samples. And of course, also you need to, when you have the IID replications, and then you can also you may want to specify the store the data set into the file, right? In the file. So in the arena, especially in the statistics section, actually you can specify the file name to collect the output analysis result, output data, so that you can analyze the data using output analyzer software. And we will do this later. Okay, output analysis. So let's talk about the output analysis. Basically, so you can use a point estimate, which means point estimate, which summarizes the sample by the single number that is an estimate of population parameter. So mu value, mean value, or variance, and so on, right? So let's say, so here's examples of n samples of x. So you can calculate the sample mean, right? And the sample variance, right? So according to these two equations, and these are the point estimate, right? Also, you can collect the interval. You can conduct the interval estimate, right? And interval means what? It's a range of values within which the true parameter lies with high probability, right? So, for example, confidence interval, right? So, interval estimating using X bar or sample variance to give you a better idea because you have an interval instead of 1 point data. So that's why you have more data, right? Basically, you have shape, right, of the distribution in a certain interval, right? So unlike the point estimate, only give you the mean value or just a variance, right? It give you the specific shape, right? And so the interval data is usually have more information. Okay, so we use a confidence interval, and then Arena also use a confidence interval a lot. And confidence interval actually is a range within which can have a certain level of confidence that the true mean false, right? So if you look at this one, actually this is the equation uh, expression to get the confidence interval on the sample mean value mu. Okay, of course you can use a t distribution. Okay, because you don't know the variance, right, of your original data set. So that's why sigma is not known. So that's why we are using the t distribution a lot. And half of it of the confidence interval is like this, right? This is these two are the half width, right, of the confidence interval, right? So we want to have a smaller confidence interval for the precision purpose, right? So this, if half width is very small, and then definitely our simulation model application has a very high precision, right? So, however, in order to get the high precision, you cannot control the t value or s value, right? Because these two parameters are associated with the process or system, right? And so you cannot change it. So easiest way to increase the precision, and you can actually increase number of applications, right? So increase an n value. By increase this value, you can make the half of it small, right? So that you can have higher precision, right? And you may wonder how many applications you need, right, to get the statistically reliable data, reliable simulation output, right? So you can use this actually equation to get the specify the half width, okay? So target half width, let's say h is a target half width, and then s is a sample variance given by your simulation model, and then t value is just given by t table, right? T distribution table, right? So, or you can use approximation approach. Replace t by z, then you can use a standard normal distribution, right? So in that case, you can use this equation, okay? And h is still target half width, and then s is a sample standard deviation from the initial run of from initial number of replications n0. Okay, usually we make 5 replications initially, or 3 or 5, okay, initially, because sometimes simulation model, single application of the single simulation model takes a really long time. I mean, it's not happen openly, but sometimes actually especially large scale simulation takes a really long time to make one application. So when I was a PhD actually student, and then I developed a simulation model to analyze the transportation network of Phoenix in US, and then since it has more than 1 million vehicles, so it takes 6 hours, okay, to make only one application of the simulation model. So in that case, I mean, you don't want to make a lot of you don't want to make many initial applications, right? So in that case, so that's why, I mean, initially you can make 3 or 5, okay, because anyway you are not going to use the result given by these initial applications. And so once you make initial applications, and then you can calculate this S value, sample standard deviation, okay, and then under the given z, you can calculate the number of n. Also, there is another approximation approach to get the statistically reliable simulation output using this equation, basically. So here, h0 is half width from the initial number of application, and then you can get the square of the half width, and this one is what, target half width, right? Target half width square, and then n0 is the number of application, right? So that you can get the appropriate number of applications, okay, to get the statistically reliable simulation output. So here is an example. So when you run the simulation model, actually 6-1, actually you let's say you use this model and then make a 10 application, okay? And 90% half width on total cost of this model is approximately plus minus 812.76, okay? And mean value is 21,000, more than 21,000, about 22,000, something like that. So we want to reduce this half width to 250 or less. And in that case, you can use the first formula and second formula. So here and there, okay? So according to the first formula, and basically you can get the 80, and then second formula give you this 106, okay? And of course this is n0, so initially we make the 10 applications. That's why you put 10 here, and this is a z-score, right? Given by this equation, right? And then h0, right? Sorry, h0, and then hs, right? So this is s, this is h, right? Okay, so based on these two results, and then you can also make you can use either this, or you can make more replications like 110. Let's say we change the number of application to 110, and then result will be like this. Okay, so although half width is slightly greater than 250, but so these two equations are approximation approaches, so it will not give you the exact solution. Got it? That's why you may want to make more application to get this kind of result. Okay, to meet this kind of target half width. Anyway, but in this case, yes, we are successfully reduced the half width from 812 to 369 or 670, 370, something like that. Okay, but if we make more applications, and definitely there will be the chance to make to meet this kind of target half width. Let's say you want to compare two scenarios. Okay, so for example, you have an alternative to enhance the performance of the existing system, and you want to compare each output with the output of the existing system, right? So in the case, you need to utilize the paired t-test. Okay, so because so in this class, I'm going to explain how you can use a paired t-test. Okay, using the output analyzer provided by Arena. Okay, all right. So usually we want to compare the alternative system scenarios, configurations, layout, and also want to conduct a sensitivity analysis, right? And in order to address these two scenario comparison case, I will utilize model 6-4, which is a simple call center, okay, as a base case, and want to increase the resource of the base case. In other words, we can add 3 trunk line, 3 each of cells, use cells, tech 1, tech 2, tech 3, and tech all. Okay, so we have a base case and then more resource case. So 2 cases. And in order to compare the output of 2 scenarios or 2 models, and you need to have collect the statistics on total cost and percent rejected. Okay, and also definitely in order to do the comparison and conduct the comparison, you need to save the output statistic to the file. Okay, and definitely we can make you can make confidence intervals, okay, on expected output from each alternative. And let's look at this total cost of the base case and then more resources case. And if you look at it, base case only have about $22,000, but more resource cases to having more than $24,500, and then even interval is not overlapped. So we can say that okay, this require more cost, right? In terms of total cost, right? It's of course because we increase number of trunk lines and add more people, so operation cost should be higher than the previous case, right? But this is not really sufficient, right? We want to get the statistical conclusion, right? That's why people conduct the paired t-test, and you can conduct paired t-test, by the way. So here, by using this paired t-test, we can evaluate whether means vary over two different scenarios. Okay, so here's the H0 and H. So the hypothesis. So in other words, the mean difference between paired observation is 0. Otherwise, different. Okay. So in this case, if you accept H0, in other words, and both scenarios have the same characteristics. Okay, you can conclude that. Okay, both scenarios have the same characteristics. So in other words, your alternative will not be accepted. Okay, because you didn't change anything. So that's why. But in terms of cost, maybe different. You may have a different story. So anyway, so in order to conduct a parity test, let's say di is the difference between two observations on each pair, such as I. Okay, and this is an equation to calculate the confidence interval for true mean difference. Okay, once you have di values, and then you can calculate the confidence interval on di. Okay. Here n is the number of samples, so number of pairs, and then the bar is the sample mean of the di, and then st is the sample standard deviation of di. Okay, so di is a difference paired set, so you can see this example to have a better understanding on paired t-test. Let's say we have two models, and then let's say we have output. Okay, so it seems like we made 5 replications to get this output from the first model and to get this output from the second model, right? Or second scenario. So this is a scenario ID, y1i and y2i, right? And the first paired set, okay, first pair, 18 and 22. So if you calculate the difference between these two values, and you will have a -4, right? 18 minus 22 will give you -4. So this is D1, and D2 will be the 1, right? Because you can subtract 20 from 21. And for the D3, you can subtract 23 from 20. So you will get the -3. Also same thing, if you subtract 26 from 25, and you will get the D4, right? Value of D4, which is -1. And we have 23 and 22, so you can have a 1 as a value of D5. Got it? So once you have these 5 DI values, and then you can calculate each average, right? So -6 over 5 will give you -1.2, okay? And also standard deviation. So n-1 will be 4, right? So 5 minus 1 will be 4, and that's a degree of freedom. And 20.8 over 4, also you can get the square root of this number, so that standard deviation of D will be 2.28. And once you have these two values, also you can, yes, in addition to these two values, you can get the t value, right? So t value is 2.78. So once you have these three values, and you can calculate the 95% confidence interval for the true mean difference. So which is 1.63. So this is given by the previous equation. Remember that, right? And then upper bound is this is lower bound of the confidence interval, right? So this interval includes 0, which means the difference can be 0. In other words, there is possible to have no difference between these two scenarios, right? So that's why we have to, if 0 value is within this interval, we need to accept H0. Okay? H0 was what? the mean difference between paired observations is 0, where both scenarios have the same characteristics, right, in terms of these output. Okay, so if you are looking for the better alternative and then got this result, and which is not the really good news, okay. Yeah, because you find a better alternative, you think that your alternative is better than the previous one, but result was the same, right? Turns out same, and then definitely you need to find another alternative, right, which is very effective. In other words, the confidence interval, if under this confidence interval does not include 0 value, then you can reject S0. Got it. In Arena, you have a software called Output Analyzer, and that software will help you to conduct the paired t-tests. Okay, and in order to do that, you have a separate the DAT files having the different statistical result. Okay, generated by Arena, and in order to save the output file, so you need to specify the file name in statistic data module. And good news is that, yes, I have a tutorial, so you can follow the provided tutorial to learn about the output, or to learn about the output and the functions in the output analyzer. Okay, so let's say you have two files for total cost and then percent rejected, and then you can compare these two outputs using output analyzer. Okay, so in output analyzer, you can create the new project and then load all the data files like this. So total cost, percent rejected. Okay, let's say you have 4 files, and then if you go to the analyzer and click the compare means menu option, and like this, and basically, and you can conduct paired t-test. But in order to do that, initially you have to add the data files, okay, which have a total cost, and then select the lumped, okay, for the replications field. And then click OK and go back to this menu, and if you choose the paired t-test and confidence level and click OK, then you will see this kind of result. All right? Yes. So if you look at the percent rejected and total cost, and both result do not include 0, right? Which means total costs are different, and then percent rejected also different, right? So reject S0 for both cases, yes. Right. So there is a statistically significant difference on both output performance measures, right?